Well, it says 12:32 on my phone, so we'll get started for those people that are signing in by live streaming. I'm Tom Annesley. That's my introduction for myself. You can look me up on Google if you want any more information. But we're here to talk about sugar curing baldness, which was not false advertising. We'll actually cover that a little bit. But in this section, I have 4 little short stories about sugar that will present aspects of sugar in a way that you might not have thought about before, in a kind of a different way than some of the speakers are going to present for the rest of the session. But we're going to start the first story over 100 years ago, back in Boston's North End. Many of you traveled to Boston. The North End 100 years ago was the main commerce area. It's the area where Faneuil Hall, Paul Revere's house, the Old North Church was at, 1 if by sea, 2 if by land, 3 if by Uber, But that's the area of Boston 100 years ago. That was the main area. And January 15th turned out to be a glorious day. They'd had 2 weeks of bitter cold weather, which we in Minnesota have. And all of a sudden, they had a break and they had the January thaw. And January 15th was supposed to be in the 50s. Right? I mean, the kids here would be out throwing frisbees and shorts, but it was a great day for the people to gather together in Boston. And all the trucks were out delivering, even those that carried liquid materials like the barrels there that weren't going to freeze. A glorious day. People had saved up their laundry over several weeks when it was cold, and the women who lived in the housing areas there, the apartments, were going off to do their wash. Couples were taking a nice walk. Children were walking their, parents were walking their children, taking advantage of this great day. Famous Firehouse 31 also took advantage of this day, and they pulled out their wagon there, and they had the officers stand in the front, and all of the firemen sit in the wagon there with their fire hats on, and the horses that they used at that time to pull their fire trucks. Look at how big those horses were back then. The captains, all 5 of them of Firehouse 31, barely reached the haunches of the shoulders of the horses. So imagine how big those horses were. But it was so glorious, they decided they were going to keep the doors open and air out the firehouse. They had horses at the time, so you aired out a firehouse whenever you could. After the picture, 2 of the firemen, Fed McDermott and Bill Connor, decided they were going to sit in the entranceway to the firehouse, and they were going to soak in some sun. And they set up a little table and some chairs, and they started a chess game. Imagine sunning yourself playing chess at noon in 50 degrees in a January. It was a perfect day until it wasn't. About 10 minutes into their game, at about 12:15, 12:20 p.m., they felt the ground rumbling a little bit. All of a sudden, they heard a major explosion, and the ground underneath, the ground underneath the firehouse shook. They ran outside to see what was taking place, and they saw a tsunami of water coming down the street. 15, 20 feet high of fluid rushing down the road. They ran back into the firehouse to warn their fellow fire officers to get up to the upper levels as quick as you can. And they were quick enough to save all of the firemen but 1. And 20 minutes later, when this liquid had run through, this is what the firehouse looked like. Now, I'm not going to go back to the previous picture, but the house that's to the right of the firehouse wasn't the original house that was next to the firehouse. Now it was there after the tsunami came through. But the firehouse actually came out better than the rest of the North End did. And this is what most of the North End looked like at 12:30 p.m. on that day. The strength of the tsunami that came through was so large that it actually bent the rails for the upper railways and crushed metal pieces and folded them around. It was a powerful event, a disaster. But what was interesting is what caused all this damage was not water. What caused all this damage was sugar, molasses, liquid sugar. It was so thick that it gummed up the mouths of the horses and the people. You can't swim in molasses. It has a far greater density than water. People just were swept away in this. Even 24 hours after the event, you can see in this photo, the firemen still standing in up to their knees in molasses. It took weeks to clear. In fact, they had to use salt water from the bay to clear it away, right? So what caused this? Well, they started looking around and they determined that the likely cause was a large storage tower right near the north end of Boston. And this was a massive structure. This was 5.5 stories high, larger than the buildings basically that were at that time that were about 4 to 5 stories. 5.5 to 6 stories high, 90 feet across, 300 feet in diameter. And it was a storage tower that was not used for housing water, but it was a storage tower owned by U.S. Industrial Alcohol. And why did they have it? And what was going on? Well, this tower was not originally made to hold molasses, but it had been filled to the top the day before with heavy, thick molasses, and that caused the disaster. And the next day, the Boston Globe noted, huge molasses tank explodes in the north end, 11 dead, 50 hurt. 2.3 million gallons of molasses ran down the street that day. 2.3 million gallons of liquid sugar inundated the north end. The tsunami turned out to be measured as high as 50 feet in some places, swept everything in its path. And you can see the destruction that was there. So then the question came about, well, why were 2.3 million gallons of molasses sitting in a tank? What would a company that makes alcohol be storing molasses for? Well, it turns out this was taking place during the wind down of World War I, and the molasses was used for explosives. So this is kind of an introduction to one of the 4 little vignettes we'll have about sugar and war, and ways in which sugar contributed good or bad during wartime in ways you might not think. Now, most of us are familiar with sugar rationing during World War I and World War II. The U-boats that Germans had were sailing off the eastern coast of the United States, so you couldn't get cane sugar from Cuba. Same thing, you couldn't get cane sugar to take over to Europe. So certainly there was rationing. 1, because we couldn't get much sugar. 2, they wanted to supply the soldiers as much as they could for sugar. But 3, a significant percentage of the sugar production during World War I and World War II went to creating weapons. War requires weapons. Weapons required alcohol as part of their explosive content. Alcohol required sugar. How much sugar beet was grown, how many people changed their habits because of this wartime. Sugar beet production increased, but here's a quote from somebody who raised it, and he said, almost the entire massive valley I grew up in converted crops to sugar beets during the war with a massive refinery built there. The main usage of sugar beets was industrial alcohol for explosives. So did you ever think about sugar being a mechanism of war, not of something that was rationed because of war? It was used in World War I and World War II for a variety of reasons by the military. One was that most of the cannon barrels, the large artillery ammunition, the washers, the dryers, a lot of the things that went into making tanks required molds. And back then, metals put into a die, the metals would sometimes stick together. So they actually coated the inside of these dies with sugar so that the metals would not stick together. And you can imagine how much sugar was used for that. Soldiers that were hurt during the war were saved by giving them citrated plasma. A lot of this was used during the war. Citrate is produced from sugar. Sugar was used to save the lives of soldiers on the front line. Sugar was a component of tobacco. This is a picture from 2 soldiers in a trench in World War I. Back at the World War I time, rolled cigarettes hadn't really come about yet, so half the soldiers smoked pipes, the other half rolled their own cigarettes, and the tobacco that they were able to get was pretty nasty tasting. even by today's standards. They added sugar to tobacco to make it more palatable. Even today, some cigarette brands contain 4% sugar in each cigarette. So a large amount of sugar was used just to make cigarettes more palatable. They now know that it helps absorb nicotine and makes cigarettes more dangerous. But then it was just to make it palatable for the soldiers. Large artillery accounted for a lot of use of the sugar. Every one of these gun barrels, when it was fired, each individual barrel used up 400 pounds of sugar to make the propellant that ejected the cannon. So, boom, 400 pounds of sugar, quarter acre of sugar beets. Boom, 400 pounds of sugar. Every time these 6 cannons went off, it required acres and acres of sugar and 2,400 pounds of sugar. And imagine how many times those were shot off during the day, right? So imagine sugar was used during the wars in a way that many of us really didn't think about, right? Now the Germans, they also used sugar. In fact, Adolf Hitler was a sugar fiend. He ate candy all day. By the end of the war, his teeth were basically rotted. He believed in supporting sugar beet production because it was good for the economy, and he wanted the economy to be good. He would go so far as to actually have himself infused with sugar solutions because he thought they would keep him awake. Each night, his personal cook would make 6 cream pies and lay them on his dresser. The next morning, most of those cream pies were gone. So Adolf Hitler was a real sugar user, and therefore he really believed in sugar production. And sugar beets was a great product there. It was used for not only feeding the population, but it was also used for explosives in the same way as the Americans and the Europeans used sugar beets to make sugar alcohols for explosion. But the Nazis went a little bit further. One of the byproducts of processing sugar from sugar beets is you end up with a byproduct called schlemp. And schlemp looks like a pile of shredded up sugar beets, what's left after the sugar has been extracted. There's a number of volatile compounds, proteins, other things that are still in this wet schlemp. And it's normally used for feeding animals. But one of the byproducts of processing schlemp further, processing sugar beets further, was a compound known as hydrogen cyanide. Right? HCN, hydrogen cyanide, which at normal temperatures can be a liquid in a vial, but it can become a gas depending on the temperature. Now, the Germans used this for predominantly delousing vats, delousing soldiers, uniforms, blankets, things like that. The US had discovered DDT, which at that time they thought was perfectly safe. But they did not want anybody in Europe to have the recipe, so the Americans used DDT. The Germans used hydrogen cyanide for delousing materials. One day, a gentleman by the name of Rudolf Hess, who was one of Adolf Hitler's lieutenant colonels, was put in charge of a little concentration camp called Auschwitz. And he figured out that he could make his camp more efficient if he could have access to some of that cyanide made from sugar beets. So he contacted the company that made the chemicals called Zyklon B, and he was able to kind of on the side, like some government officials might do, get a supply, maybe slide off about 5% of the cyanide production, and he put it to a much different use, gassing Jews. So the sugar beets, the product of the sugar beets, were used to make hydrogen cyanide, which was used to gas people in the concentration camps. Kind of an interesting aspect of the use of sugar. The cyanide was called Zyklon B. The can was labeled gift gas, which I think is kind of a bizarre thing because there was no longer a gift to those people. But gift gas means dangerous gas, poisonous gas. So that was actually a warning sign, essentially. Okay. Now, not all the sugar use in World War II was for war materials, for a negative use. There was actually candy production that was able to ramp because of that. And M&Ms was one of the favorites that were sent over to the troops. There were things like Hershey bars at the time, but you can imagine what a Hershey bar is like in a soldier's pocket out in the hot sun all day. Most of it's on their uniform. Hershey bars, when they freeze, it actually chips off and they end up losing half the Hershey bar. So there was a need to somehow create chocolate that was immune to the hot and cold environments of fighting in Europe. The Mars Company came up with something called M&Ms. And their product was unique in that they had chocolate, but they had figured out a way to coat the chocolate with candy. So therefore, even if the chocolate got hot and kind of melted, the candy coating kept these M&Ms fairly much intact. Okay. Now it turns out that making M&Ms is quite laborious. They're trying to chemically link two types of candy and sugar together. The drying process is quite laborious. It turns out that there's a lot of actual chemistry going on in making candies. So the M&M, Mars Corporation, has over the years wanted to seek out experts in consulting, chemists that could help them out in figuring out different ways to combine sugar. And one of their consultants is Los Alamos Laboratory, right? Los Alamos, what's everybody associate Los Alamos with, right? The same company that helped Mars develop M&Ms is the same facility that helped you develop the atomic bomb. Not only that, and this is one of these things you can't make up sort of facts, the lenses for the atomic bomb were made by creating special materials and metals at the bottom, rounded bottom of a container. The container that worked best turned out to be a confectioner's candy kettle. So a candy company relied on the company that made the atomic bomb, who relied on a candy company to give them the machinery to make the atomic bomb. Who'd have thought sugar would have come that far, right? Now, one of the individuals who worked on the atomic bomb was an individual named Richard Feynman. Remarkable individual. He was one of the funniest people known. He's written a book called Surely You Joking, Mr. Feynman, if you ever get to read it. And he was a physicist, and when he was done working with the group in developing the atomic bomb, he went out to California, and he wanted to study quantum electrodynamics. Now, I'm not a physicist, but quantum electrodynamics to me is electrons which circulate all over. Electrons are what keeps the world going. Without electrons, we're all going to collapse. But electrons cannot collide with one another and basically create disastrous reactions. But they occur in nature, and Richard Feynman wanted to know, how do electrons interact in such a way that they kind of affect one another, but they don't collide and cause the world to basically implode? And there were two mechanisms that he thought. One was what was called electromagnetic, and one was by photometric. So potentially light beams that were given off. Another one was an electromagnetic intention. But all he knew at the time was that electrons circulating the atom would get close to each other. Somehow they would interact, but they kept their intactness, and they're able to go off again and do their own thing. And he said, well, I'm a physicist. I'm going to come up with these mathematical formulas to describe what's happening. And he came up with a formula like the one on the top slide here. Not simple by my mind, anyway, right? He went further and said, well, there's a lot more that can happen when electrons interact. Here's another equation that I've come up with that includes voltage for electromagnetic, photon, things like that. And even went so far as to come up with complicated equations like this one here to explain what he thought was taking place with electrons. But all he knew was essentially electrons would come together, and in this magical cloud that nobody knew about, they would interact, and yet they would leave intact. And at that time, physicists really didn't know what was going on. One day, Richard Feynman went into his bathroom out in California, and it probably looked like this. This is an actual bathroom from an apartment that was in his complex at the time. And he noticed ants crawling around in his bathtub. And you can see ants crawling here. You can kind of see with the white line, kind of a little trail of pheromones or chemicals that ants and insects leave when they're crawling around. Now, I suspect that most people in this room, if they saw ants crawling around in their bathroom, would go out and buy a can of Raid. And this is actually a can of Raid from the 1950s where they didn't have the fluorocarbons and spray stuff. You had to mix it up, put it in your thing, and around the area. But no, Richard Feynman, Raid wasn't good enough. He passed right by the utility closet, went down to his kitchen, and grabbed sugar. And on his way back, he went to his office, and he picked up a packet of colored pencils. So instead of killing ants, he decided he was going to use sugar for his experiments. So he took and he put a sugar cube at one end of his bathtub, farthest away from the little hole where the ants would crawl into their nest, and he waited for an ant to come along. And the ant discovered this sugar, right? Sugar and ants are like magic together. And the ant immediately went back to the nest to try and tell its buddies that there was sugar out there. And it kind of crawled around in a, somewhat straight path, but it wandered around and kind of like the little line that you saw in that previous slide I showed of ants. And a second ant came along, and it took a little bit different path, a little bit straighter. It actually would go so fast sometimes that it would slide from the path of the first one through another path, get the scent again, interact with the pheromones of the previous ant, but then get back to its own paths. And it was a little bit straighter path. The third ant, the fourth ant, things are getting a little straighter, right? There's an interaction, but it's getting better. Fifth, sixth, seventh, eighth, ninth. By the 10th ant, they were basically going in a straight pathway. And he looked at that and he said, that reminds me of what I think is going on with electrons. They got to interact somehow, and electrons have to somehow impact the path of one another, affect it, and in the same way as the paths don't kill the ants, the electrons don't actually hit each other and destroy each other, but somehow they carry on, have a relationship, and then go back in their normal ways. And he took the summation of his ant diagram, and it looked like that. And he said, kind of looks like what I think electrons are supposed to be doing. But he went back and he said, I've got all these equations, but they're too complicated. And I think it would be much easier for me to figure out what was going on with sugar and ants and electromagnetism if I can create diagrams. So for example, on the left here is an equation of a triangle. The triangle is on the right. Now, right, if somebody asked you, draw or describe a triangle, you would draw the figure on the right. You wouldn't put these equations on. And Feynman decided that figures were the best way to prove his ant theory. So he came up with hundreds and hundreds of diagrams, each of which matched from the simple to those long equations I showed you. And he found that some of the diagrams, like the one in the center there with the two parallel lines, the electrons came close and they kind of interacted and sped each other up, but they really didn't have a major impact on one another. That probably occurred about 0.01% of the time. Then he looked at other ones, such as the one in the upper right, where one of the electrons got close enough to the parallel electron, released a little bit of photo energy, gave off a little bit of a photon, but then reabsorbed it again, so it kind of deflected its angle temporarily, but then both electrons safely went on its way. So you could use photodynamics and still explain why electrons didn't collide with one another. And he took those diagrams that on a statistical basis represented the most common ones. Some were 0.01% of the time, some were cajillionths of the time. And he said, I'm only going to worry about the ones that occur up to about 1/trillionth of a time. I'm not going to worry about the other ones. So in the same way as we think about pi, the number that keeps on going, as 3.14, by the time you get to the trillionth number there, we've kind of gotten all the information we need, right? Now, physicists today with computers will go out further. But back then, if you could calculate something to the 10 trillionth, you were pretty good. And he said, I think that's what's happening in photo and electromagnetism can be explained to that extent. And when he finally came up with his composite diagram, this is what it looked like. Kind of looks a little bit familiar because that was the ant trails. So the trails that the ants had created in his sugar experiment mimicked the diagrams that best describe what was happening in electromagnetism. So drawing ants to a bathtub with sugar instead of Raid was an interesting experiment. He ended up winning the 1965 Nobel Prize for what I call coloring with ants, essentially. Feynman lived into the 70s. Had he lived longer, he would have loved to taken one of the first rockets to the moon. In fact, he was involved in a lot of the original space shots. He was also involved as the person who explained what happened to the Challenger when it exploded in 1983. He was the one who had the theory for it, essentially, and then he died next year. But he always wanted to go to space. So that kind of leads into another part of our presentation, part 3, which is sugars in space. Now, we all think of what takes place on Earth, and we don't think about the fact that could there actually be sugars out in space? Turns out there are, and they have a function. In 1999, after New Horizons 1 ended its probe, NASA sent off the Horizons 2 probe. And it was to be a 6-year mission to reach the farthest ends of our solar system. And in 2012, the New Horizons probe made it to Pluto and took pictures. But they realized at the NASA headquarters that the New Horizons probe still had a little bit of energy left in its system. So they did what we do today by programming a GPS into our car. They sent new instructions to the New Horizons, and they said, just keep going, and we've got something in mind that's kind of far away. In fact, it's 6.5 billion kilometers from Earth. Pluto was about 3 or 4. We want you to go to that planetoid or what's out there because it's just really unusual looking. And it took the New Horizons 3 more years to travel the 2 billion miles until it got to its final destination, which was a red planet, as it turns out, called Arikoth, which was given its name in tribute to the Native Americans that were living in the area at the time. Arikoth was unusual in that it kind of had a dumbbell shape, but unlike most of the gray planetoids and most asteroids that they saw, Arikoth was actually very, very red. Why was it red? Well, they knew that Arikoth had a frozen environment. They knew there was methanol surrounding it. They knew there was ammonia. There was nitrogen. But methanol, ammonia, they don't have color. It's colorless. So what would cause a red color on the moon? They theorized and then proved over the next few years that the red color came from a class of compounds called tholins, which can be thought of as a group of carbohydrates. They're basically sugars. And here they had discovered a planetisma, which is what they call small planets, 6 billion miles from Earth, that was coated with frozen sugar. Now, they needed to prove this, so they did experiments here on Earth where they reproduced the conditions around Arikoth. And they created radiation sources, high energy beam sources. And what they did then is they took methanol, ammonia, nitrogen, other things, and they cooled that to minus 233 degrees centigrade, minus almost 500 degrees Fahrenheit, which mimicked the frozen conditions out 6.5 billion miles back in the Kuiper Belt. And then they shot a lot of high energy beams, high energy electron beams. And these were high energy beams because they needed to mimic what happened over hundreds of millions of years in a 1-year grant. So it's kind of like, yeah. We wouldn't get a grant today for millions of years, but anyway. So they did that, and then they analyzed what products were produced, what products coated that chamber. And they found basically a red liquid tar. And in that red liquid tar, they found a bunch of sugars, including glucose and ribose. Now, ribose is kind of interesting because many of you have probably heard about ribonucleic acid. It's the sugar, ribose is a 5-carbon sugar that's responsible basically for life on Earth, right? RNA, ribonucleic acid. Proteins are produced, and then that's part of the origin of life, simply. Another sugar that has been proposed and proven since then to most likely exist in these outer space conditions is deoxyribose. And you all know DNA, right? Deoxyribonucleic acid. Deoxyribose is the sugar in DNA on Earth. And yet it existed billions of years ago, 6 billion miles from Earth, right? Now, deoxyribose kind of turned out to be interesting because early experiments past 2020 found that one sugar could cure baldness. And that sugar turned out to be the same deoxyribose as in DNA. And the way they came about that was from studies that were done on wound healing in rats in about 2022, where they would make an incision in a rat, and we're not going to discuss animal experimentation, but on the far left, they created a nickel-size incision, basically a nice gouge in the skin of the rat. And then they applied just the vehicle, an alginate, which is like a seaweed-type material, and they applied an alginate, a topical gel, that contained 5 or 10% 2-deoxyribose, the same sugar as in DNA. And what they found, what you can see is after 10 days, how well the wounds healed when they were coated with deoxyribose compared to the second one where the wound was just left open. So within 10 days, these wounds basically completely healed and were scarring over just from adding deoxyribose. The theory was that deoxyribose causes revascularization under the skin. So the more blood vessels that it can help generate, the faster the healing process, to put it in simpler terms. Another group in Europe picked up on that and said, all right, we're going to think of something really interesting. Does deoxyribose cure baldness? So they did experiments where they treated mice. I have to preface right away and say a lot of the baldness they investigate is what's called male pattern baldness. It's from high levels of testosterone. It's different than female baldness. So basically what they did is they treated rats with testosterone to load it up as if it was like a male who had a lot of testosterone and was going to become bald essentially, and then they shaved the skin. And they kept giving the testosterone to mimic what would be the worst conditions for causing a male to go bald essentially. And they gave these rats either a control gel or a gel that had 2-deoxyribose in it. And it turns out the 2-deoxyribose reversed the baldness. It's a little difficult to see, but on day 14 on the left are the rats that just got the gel, and you can see the shaved silver portion of it there. The rows that received gel plus 2-deoxyribose had about 60% of the hair come back. By day 21, the rats that had not been treated with the sugar essentially still had bald spots. Those that had been treated with deoxyribose had almost full hair growth. So sugar reversed baldness. Who'd ever thought of that, right? There's even products which have come out in the last year. I just have one that's available there. They're just starting to do studies on it, obviously, because this came out just 1 year ago exactly at the end of September. So there's studies to be done. Now, I'm sure you're thinking, you know, Tom Annesley's trying to describe to you something that took place way out in outer space, and you know, you're going to tell me that there's something in outer space that's related to DNA and reproduction that causes hair growth. Where's the physical proof? I've got it for you. Now I'm going to show you in the next picture some physical proof, but I got this picture from government archives from Roswell, New Mexico. Right, Roswell, New Mexico is where the alien was found a number of years ago. So I'm going to show you this picture, but you got to remember that it's secret. You can't share it outside this room. When they found the alien at Roswell, New Mexico, he looked like this. Okay? The sugar in space caused him to grow hair. But who'd have thought about sugar in war? Sugar attracting ants proving a physics therapy that really ended up with a Nobel Prize. Sugar in space, one of those sugars cures baldness. All right? So we're going to finish up kind of something different than what was presented earlier. A lot of the speakers this morning have talked about sugar content in things, and the sugary drinks in the world have kind of gotten hit pretty bad. There's been a lot of pictures of Coca-Cola and things like that, right? And again, it's all in portions. When I was young, you got a 6-ounce bottle of Coca-Cola. Now you get a 16-ounce bottle, which contains roughly half of that content of sugar, right? But as much as sugar gets a bad rap and colas get a bad rap, it turns out that the cola companies, including Coca-Cola, made positive contributions to the civil rights movement. How many of you have ever been to Atlanta, right? They have the Coca-Cola Museum there, right? One of the biggest industries in Atlanta is Coca-Cola. And if you think back to the 1960s, before there was the Atlanta Falcons, the Atlanta Braves, Peachtree Plaza, CNN, and a lot of the financial institutions, Atlanta was synonymous with Coca-Cola. Without Coca-Cola, there was going to be no Atlanta, basically. And in 1964, a native son of the South, Martin Luther King, won the Nobel Peace Prize. This is him giving his lecture, his speech in 1964. And when he came back from receiving the prize in Oslo, a group of people in Atlanta got together in a committee that was headed by the mayor, Ivan Allen, and the CEO of Coca-Cola, Robert Woodruff. And they said, this is the perfect opportunity for a city in the South to show that we're beyond the negative things that are happening at this time in 1964, right? All the angst around integration. And they got a committee together that included a rabbi and some students, and they decided they were going to host a dinner for Martin Luther King. And they sent out 2,000 invitations to business owners, scientists, anybody who was a who's who in Atlanta, including a lot of the black business owners, people that were influential in the city, but predominantly, obviously at that time, the power was in the hands of the whites. And they invited these people to a dinner at the Drinkler Hotel, which I actually was in years ago before it was torn down, to honor the 1964 Nobel Prize winner, Martin Luther King. They sent out thousands of invitations. If you raise both your hands, this is the number of respondents they got. 10. People just thought this isn't the time for that, essentially, right? Even Martin Luther King winning the Nobel Prize he was a son of Atlanta, but he wasn't really a son of Atlanta, right? He grew up there, but he really wasn't a son of Atlanta, essentially. So they started over again, and the mayor of Atlanta sent out letters. He went on television, and he said to the business owners, the mayor of Atlanta is going to be at this dinner. The rest of you may come up with excuses about I'm out of town and I'm sick, but he says the mayor of Atlanta is going to be there. They got a few more responses. That really cheesed off the Coca-Cola Corporation and Robert Woodruff. He started a campaign. He wrote thousands of letters to businesses. He had ads that he was ready to put into the Atlanta newspaper so the people knew that this would be coming out. And he wrote the following: it's embarrassing for Coca-Cola to be located in a city that refuses to honor its Nobel Prize winner. We are an international business. The Coca-Cola company does not need Atlanta. You all need to decide whether Atlanta needs Coca-Cola. Had Coca-Cola left, Atlanta would be a totally different place than it is today. That was what it took. And they ended up getting 1,500 responses after that because of the threat of a sugariest coal in the world on behalf of a Nobel Prize winner. So they ended up having the dinner on that date at the Dinkler Hotel. 1,500 people took up 2 floors of the hotel. It was so packed that by today's standards, it would have been a horrendous fire hazard, but they got away with it at the time. And Martin Luther King gave a talk to this essentially integrated audience. And the newspaper reported the next day that the crowd, including many of whom had never dined with a member of the opposite race, even broke out into an impromptu rendition of "We Shall Overcome." And the famous line that came about that time, "Atlanta, the city that's too busy to hate," is still there. And that took Atlanta off because the sugariest drink in the world decided it was going to get involved in the integration movement. So imagine sugar and war in ways you never thought about. Using sugar to attract ants in a Nobel Prize experiment. Sugar in space, one sugar of which reverses baldness. And the sugariest soda company in the world helping to integrate Atlanta. Think of that. So, I'm Tom Annesley. Thank you for coming. And hope you enjoy the rest of the talks. You're welcome to leave. They did say since it's live streamed, they might have some questions and things. If there are no questions, we'll go back and listen to some good music.
You do a very nice job of putting together lectures. How do you go about that? What's your methodology?
A lot of. The question is, I present good lectures. Thank you, Uncle Phil. How do I go about my methodology? Well, a lot of it is experience. I do a lot of research on the topic, again, because of the way I write, to look at things in a different way, right? If you're going to write a story about person A, there probably was a person B in that person's life that needs to be told about. So if you're going to think about sugar and slavery and the rest of it, there's got to be interesting stories about sugar that remain told. It probably, but it probably takes me about 100 hours to come up with a lecture like this because you're doing research and things like that. But it's just a matter of put it in your mind about think in a different way. Think about how something has not been presented before. And you find that the material is out there. It really is. Everybody gets on the internet and looks at all the common things, right? But think about something that might be unusual and research it, and the answers just start popping up of interesting things to talk about. So that's how I do it, and I'm just lucky, to be perfectly honest with you. So I also got to teach a fair amount when I was my first class was in this room in 1975, this very room. But they got me teaching early. They, several times during the year, would come up to me and they'd say, "Dr. Jensen is sick this week. You're teaching analytical chemistry this week." You had to do it. And it was like, you learned you could do it, basically. That's where somebody trusts you to do something, has confidence in you, and you kind of build your own confidence. I mean, that's why a college like Gustavus is so special with the mentoring and things like that. You know, so I can't take credit for it. So, but that's the answer. It's just preparation, but just pure luck sometimes, to be honest with you. Thanks, Uncle Phil. All right, no more questions. Enjoy the rest of the day. I hope to see you around, and thanks for coming. And thank you for coming, Rick. Well, you know, but I say the same thing about it. I came to about 90 kids who were sick. I thought, this guy is a fiddle. I thought you were very silly. All right, see you later.
That was great.
Thank you. No, that's not me. No, you can pass things out. People don't come here to be, you know, to pass out for a book. So I thought they could, it's in the program. That's not my style.
Our copies are very
They are not. They're all.
What's your PhD in?
My PhD, biochemistry.